entitled The Neutral Point Method for Addressing Missing Data in Multimodal Kernel Fusion Problems. So this is a methodology I developed in conjunction with some collaborators at the Russian Academy of Sciences and Tula University. Some years ago now, but it's been more recently applied. So I don't know what people's level of familiarity is with stochastic pattern recognition. So before getting into the maths of the neutral point method, I'll just go through the sort of very basics of stochastic pattern recognition. So traditionally this is built on a feature space representation. So you typically have objects or individuals, and they're associated with those a number of measurements, which can be integers, binary numbers, real numbers, something that you can embed upon the number line. So when you have a set of these measurements, you can embed any particular individual into a feature space as a vector. So in this example, you've got 3 people that each got an age and a weight, possibly other measurements, but we're only showing 2 features in this particular instance, and we can embed those individuals in the space. So that would actually be trivially simple for most pattern recognition problems. I mean, in something like a computer vision problem or an image processing problem, you've got feature measurements related to the nature of the image and you have dimensionalities of millions. So those would typically be the challenges. And the goal of classification, you can also do regression obviously in the vector space, but the goal of classification is to find an appropriate discriminator in the feature space. So in this case, you're equipped with a set of feature vectors with a class label. So you can see here they're just coloured red and blue to indicate class membership. So this might be, in this case, something like diabetic, non-diabetic, or perhaps potential for diabetes, or at risk of. So the idea of classification is to find a way of dividing the feature space so that you can attach a discrete label, class label, to any new feature vector that happens to come along. So if a new individual happens to come along that has a set of measurements, the same sort of feature measurements as you have in your training data, then they're automatically embedded in the feature space. And by virtue of appearing on one or other side of the decision boundary, in this case it's a linear hyperplane. So the hyperplane always has a dimensionality of 1 less than the dimensionality of the feature space. So by virtue of having bisected this space, you're automatically attaching a label to this new incoming object. So any one person comes along, in this case, they've got an age, they've got a weight, they appear as a vector in the space, and consequently you can then label that individual as being either diabetic or non-diabetic. So the goal is to find the best discriminator, and there are a lot of different strategies for doing that. So probably the state of the art at the moment is the support vector machine. And many others, this is the accumulation of a long history of finding appropriate discriminators. But the support vector machine is the current state of the art for, I'd say, 3 particular reasons. It has a very low structural risk. So typically when you're building a classifier, you have a bias variance trade-off problem. So bias is the extent to which a classifier exhibits or fails to respond to training data. It's only intrinsic stiffness, if you like. But that's contrasted with variance, which is the response to training data. So clearly, you've got some trade-off between the two. If your classifier has too much freedom, if it's too flexible, so typically this is manifested by having too many free parameters associated with the classifier, then you will overfit to the data. You will fit to either the noise component of the training data or just the sample, just the sampling nature of it, sample bias, because you're not getting a true representation of the underlying distribution, and the training data is all you have. So you don't want to over-respond to the sampling issues, but equally you don't want to be inflexible with respect to that. So but in the bias-variance trade-off, there's an optimum point where basically you have the lowest structural risk, where in other words, your classifier is going to generalize as well as it possibly can. So typically this means you're allocating enough free parameters to the problem. And because of the nature of the support vector machine, which I'll go into shortly, it has an intrinsically low structural risk. It's also the optimization problem that you're solving to find the support vector machine discriminator. You're solving a convex optimization problem. So, in other words, you have no local minima. You always end up with the same solution. It means it's well behaved, and there are lots of ways of speeding up the whole process of arriving at the optimization. So that's also a very desirable quality. But I think principally, the reason it has become the workhorse of pattern recognition is because it can be extended indefinitely via the kernel trick. This is something I'll explain shortly. But the basic non-kernelized support vector machine essentially tries to find the maximum margin hyperplane. So you can see in this example, you've got the linear hyperplane, and the margin is effectively the gap between the hyperplane and the nearest instance of a particular class on either side of the boundary. So a support vector machine, very simply, tries to maximize the margin. It finds the discriminator that maximizes that gap, and that finds, but always finds, a unique hyperplane. And crucially, it does so by, with respect to just a very few objects. So although you may have many training vectors, you're only interested in those few objects, or the decision hyperplane is only defined by a small handful of objects, known as the support vectors. And this is the key to its low structural risk. I mean, it is a discriminative classifier, which means you're not wasting free variables in trying to model the underlying distribution of pattern vectors, which is often the case in many sorts of classifier. You're actually trying to model the distribution in order to build the decision hyperplane. But here, you're not attempting that to do that at all. You're building a discriminative classifier. You're only attempting to differentiate between the two. So there's no modeling whatsoever of the actual intrinsic distribution of vectors. You're only modeling, effectively, the gap between them. So these very few support objects are the key to its low structural risk, because you can imagine a very high dimensionality space where you've got relatively few sample points. So clearly this is going to be a problem if, for any sort of classifier that is generative, that is modeling the underlying distribution. If you've got a computer vision type problem where you've got feature space dimension in the millions and maybe just a few instances, training instances, for many types of problem, that would be ill-posed. You would have too many unknowns and too few equations to solve it. For instance, you couldn't fit a good Gaussian model. If you have just 3 sample points in a million-dimensional space, there's no way you can fit a Gaussian distribution with its covariance matrix and mean to that distribution. But here you can always get a solution, whatever the sparsity is, in your high-dimensional space. But crucially also, the optimization, and we'll come to this later, the optimization problem is written in terms of vector inner products, which means it can be kernelized. That's, in other words, the application of the kernel trick, which I'll explain in more mathematical detail shortly. So, kernel methods then differ, really quite a paradigm shift in classification, but also in regression. So regression is just model fitting. So wherever you're model fitting to high-dimensional data, the kernel methods are equally applicable there. So basically, standard pattern recognition involves a given feature space. So in that diabetic example, every individual that comes along has an age or weight. So they just fit straight away into a feature space. On the top right there, you have the Fisher Iris data set. This is very much the original data set. that in which classification is a problem is mathematically derived. And that's straightforward. Every single object has the same set of feature measurements.
In your previous slide, if you just have completely random data points, does it still give you some kind of line?
You will always get a solution. Obviously, if you have a uniform sampling from a uniform distribution at random, it's going to be an entirely spurious.
Yeah.
So literally, it will be taking the sampling, the error or the sampling bias, and just building a classifier on that. It would be completely meaningless in those circumstances because it's absolutely not a separable problem. It's not even a classification problem is specified. So the difference here is that in many situations you don't actually have a given feature space. One particular example, as a motivating example, would be genomics. Genomics, DNA strands. You'd like to perform classification and regression with respect to DNA strands, but DNA strands are labeled sequences, in effect, of arbitrary length. It's typically a very high length. But it's not the length per se that's the problem in terms of dimensionality, it's the fact that this length can vary. So you can't readily represent, or at least you can't immediately represent, a sequence of labels of arbitrary length in a standard feature space, because of the intrinsic dimensionality difference. But what you can do is carry out comparisons. You can measure the similarity between two DNA strands using, for instance, edit distance. So the edit distance is the least number of edits you would have to apply from one DNA strand to get to another DNA strand. So, where an edit can be either changing an amino acid base or adding a new base or deleting a base. So basically you can find these measures of comparison. Another one might be the the most recent common ancestor. If you imagine these two DNA strands mutating from a single ancestor, how recently in the past would that ancestor be? And that gives you a measure of similarity. So given that you can make comparisons of objects, it would be nice to be able to do classification and regression just with respect to comparisons. So when you're applying kernel methods, in contrast to standard machine learning, what you have is a similarity function. So it's a similarity function defined with respect to all pairs of objects in your training set. So in this example on the top right, this is simply an inner product between the symbol represented as a low resolution image and the corresponding symbol in the matrix. So for instance, on the leading diagonal, you have complete self-similarity. So the inner product between the symbols is obviously unity multiplied. It's very easy to vectorize an image, by the way. You just concatenate it, and you can perform a vector dot product. Where the symbols are completely dissimilar, you get what's represented here as y0. So there's no similarity. Most things are somewhere in between in the grey scale, sort of diamond circles are approximately similar, or have roughly 50% similarity. So that's what you're given in a kernel regression problem or in a kernel classification problem. Obviously along with a set of labels if it's a classification problem. So you have a particular discrete label associated with each object. And the point of kernel methods is that you can always demonstrate, I'm going to make this clearer later, is that you can always demonstrate that that kernel matrix is equivalent to an inner product of two vectors in some different vector space. So you may not even have started from an initial vector space, you might just have comparisons like the genomics example. But basically you can always demonstrate that the kernel matrix is equivalent to a gram matrix, which is a matrix of inner products between all pairs of entities. And crucially, that is linear. It's a linear Hilbert space. It's got very well-defined mathematical properties. So a kernel method is implicitly creating an embedding, provided the kernel similarity function obeys certain mathematical constraints. So you can't just have any similarity function. They have to obey Mercer's conditions.
Is this phi given?
So
Is this phi given? This.
this is the interesting point. As I'll show later on, actually, in fact, no, you don't have to ever worry about what phi actually is, and this is one of the beauties of it. I'll make that a little bit clearer shortly. So for the kernel support vector machine, you don't actually need to calculate the feature map at all. So what you're doing in this case, you're doing the linear SVM, you're defining a linear hyperplane in your embedding space. So if you had some sort of input space, now depending on your choice of kernel function, that it can be a completely linear to non-linear mapping. So the support objects in this case, you see on the bottom far right, the support objects are still defining the decision boundary in the input space. So we've got a linear decision hyperplane in the embedding space, but in the original input space, this is now something much more complex, and the particular form that takes depends on your choice of kernel. So this is very interesting straight away, because typically if you're doing any sort of classification that involves creating one of these very complex, wiggly decision boundaries, you're going to be adding a lot of free parameters. And free parameters are dangerous in classification because of the danger of overfitting. The structural risk that would be associated with that. In other words, it wouldn't generalize from your training set to some new data set that came along. But in this case, you can see that actually, although this decision boundary looks complex, it's certainly not linear in your original input space, it actually is defined by the same set of support objects. So, in other words, its actual parametric freedom is still just as low as it is in the embedded space. So this is why the support vector machine is the state of the art, because of this freedom. If you have a good kernel providing it for Bayes-Mercer's conditions, then you can redefine your problem in any number of different ways. You can keep experimenting until you find one that is suitable for your problem. I mean, for instance, you can do very useful things, and this is a very common first choice of kernel. It's to use a radial basis function, which, when you're given a linearly inseparable problem, like the problem on the left, you can see there's no decision hyperplane that will separate your classes. If you apply a radial basis function, you can always guarantee to project that into an embedding space where you do have linear separability. It might be an infinite dimensional space, but it's still linearly separable. And the great thing is, because although the space might be infinite dimensionality, it's still only parameterized by the kernel matrix, so there's no extra complexity in there. There's no you're not adding any new information. So the problem I'd like to discuss for the bulk of this talk is what you do when you have multiple modalities with missing data. So maybe a motivating example of this would be medical healthcare analytics. So for any one individual patient, you might have a series of different modalities of medical measurement. You might, for instance, have MR scans, you might have blood pressure readings, you might even have handwritten notes from a doctor or a GP. So potentially you can find a kernel in each of those domains. There are kernels for comparing text, there are kernels for comparing, that can use to compare images, kernels that can compare label sequences, something like the edit distance. So you can build a kernel in each of these individual domains. And what you'd then like to do is to do some composite classification. But the problem is that in a domain like medical analytics, chances are you're never going to have all of that information at the same time. You might have one individual who's got blood pressure readings, but no MR scans, another individual has MR scans and no blood pressure readings, and so on. So you've got a problem of missing intermodal kernel measurements. Now that isn't so much a problem in standard pattern recognition. If you're doing standard pattern recognition, you could use things like mean value substitution. You could just fill in the missing blanks, in effect, using sufficiently unbiased assumptions. But the problem in approaching this from a kernel perspective is that your decision space, or your regression space, is defined by the kernel matrix, defined over the vectors. And that means missing data is potentially a problem. You don't have a given space in which you can substitute missing values because you are creating the space in effect using your values. So it's a completely different way of thinking about the problem. So the actual Mercer embedding space itself is derived simply by eigendecomposition of the kernel matrix. So if you eigendecompose the kernel matrix so that it becomes a matrix product, U lambda, U transpose, where lambda is a matrix that has the eigenvalues on the leading diagonals, and U is the vector, and U is the matrix of eigenvectors. That gives you the basis of the embedding space.
I'm assuming that this K is symmetric?
Yeah.
Okay, so
that's always the case. In fact, that's one of Mercer's conditions, as you can see here. So if you're doing multimodal classification, what you want is a composite kernel. So that's formed from the component kernels. So I'll call those K sub I, so each modality is labelled I. So what you want to do is build a composite kernel from your constituent kernels. And that composite kernel has to be symmetric, continuous, positive, semi-definite. So in other words, it's got to have non-negative eigenvalues in the eigenvalue decomposition. So there are lots of ways, in fact, of combining kernels that do obey those constraints, Mercer's conditions. The simplest one of which is a linear sum over constituent kernels. The sum of kernels is still the kernel, which is useful. But obviously, you can't build that composite kernel if you don't have corresponding objects in all modalities. If you're missing, if some object doesn't have data represented, you can't put a blank in because you have, it would be a row and column blank within the kernel matrix, so you couldn't do that composition.
So what was the point of substituting with means then? Using means to create the...
Well, because the mean of what? I mean, what you're missing in effect is a row and column of the kernel matrix. So to know what values to substitute, you'd have to know a good deal about the composite embedding space, which in fact I'll discuss shortly. If the eigenvector, if your feature space is already given, then you can start to work that out. You can average over it. It's a lot harder when you're lacking the space. The missing object, potentially creates a space of completely different dimensionality. So you can't, you're combining completely heterogeneous things together. So what's generally done is to treat this as a decision fusion problem, a classifier fusion problem. In other words, if you've got missing data, what you would do typically is build a classifier in your individual domains, in your individual modalities, and then you would combine the decision outputs together, which can be a good strategy because there's a whole science of decision combination. You can often show that combining decisions is a good thing to do because you get error cancellation and so on. But we obviously want to, but it's obviously not as good as being able to find proper substitutes for these missing values. So that's the sort of broad background. Drill down a little bit into the maths now. In kernel methods, you effectively have two sets of choices to make. You have a decision about the choice of kernel and the decision about the choice of regressor or classifier. And the nice thing about kernel methods is it's completely modular. You can use any kernel with any regression or classification algorithm that is subsumed by the kernel methods. So common kernels that are applied generically include there's a radial basis function on the top left there, below that polynomial kernel. So those can be built on top of an existing vector space. And obviously there are bespoke kernels like equidistance for genomics or something. And you can invent your own kernels, providing it leads to continuous positive semi-definite eigendecompositions. You will fulfill the constraints. So sort of common kernel algorithms are, well, the support vector machine that we've indicated, Fisher discriminant analysis. So Fisher discriminant analysis is simply the decision boundary that's built by assuming that your data is distributed as a Gaussian, so that the class distributions are Gaussian. In other words, you measure the mean and covariance of the individual classes, and that allows you to then find an optimal decision hyperplane, which would be perfect if your data were Gaussian distributed, but in practice that's almost never the case. So it's an approximation, but it still sometimes produces good results, and probably prior to the support vector machine that would be the optimal classifier, or at least the first resort classifier. Kernel regression is something you can do. So this is where you're actually trying to model the underlying distribution with kernels. So you're not necessarily just classification problems. You can also do kernel PCA, kernel CCA. So PCA, principal component analysis. That's where you're doing principal component analysis in the embedding space rather than in your original space. So you can choose an arbitrary kernel, and then you can but also canonical correlation analysis. Is this from outside?
No, it's not.
No. So anyway, so you can do PCA, you can do principal component analysis in your embedding space. So you apply your kernel first. So this is our rate money going into the council's party. So canonical correlation analysis equally you can do in whatever embedding space you've created by the choice of kernel. So just to give it a formal definition, a kernel is a symmetric, finitely positive semi-definite function maps between two objects into real valued output, similarity. And the fundamental theorem of kernel methods is that basically you can rewrite that function, as you say, as the inner product of these two vectors that are essentially feature maps into, so phi is a feature map into this embedding space from your original object, and phi, having generated a linear vector, the kernel can be shown to be equivalent to a dot product between the two. So
This is what you were saying, the embedding into the Hilbert space.
Yeah. Yeah. So the kernel trick is whenever you've got an optimization problem that is written in terms of a Gram matrix, and you can tweak quite a lot of types of optimization problems so that they're written in terms of a Gram matrix, which is the inner product of entities in some vector space. Then you could substitute that with an arbitrary kernel matrix, and the optimization problem will still be essentially the same. So you won't have to solve a different kind of optimization problem. You can apply whatever optimizer you were using. And also, the kernel trick implies that you never actually have to do that, perform that calculation of what the actual feature mapping might be. So you never actually have to carry out the eigen decomposition yourself, which is an expensive process. So you can just substitute, you can just literally substitute your Gram matrix with whatever kernel matrix, providing it does obey versus constraints. Then the feature map is computed for you. So to make this more concrete mathematically, you've got a set of kernel measures k sub I acting on sensor outputs. So in this biometric problem, you can see the heterogeny here. You have x sub 1 being a face image, x sub 2 being an offline signature, so in other words, just an image of a signature. X sub 3 is an online signature. This is where you've got a pen that models the actual vector movements, so you get speed and so you get a range of additional information over a standard signature, although it does obviously slightly affect the dynamics of the pen. X4 might be a fingerprint, X5 might be an answer to a question. So, it gives an idea of the sort of heterogeneity you can deal with. You can actually have responses in there, as long as you can build a kernel function to compare different responses. Then you can build a kernel that embeds the individual sensors into a linear space. So basically, what you end up with is a set of embedding spaces, X sub I, for the individual domains. So the classification problem is then completely defined by the training set consisting of the kernel matrix, along with the class labels associated with the objects. So if you have n objects, you've got an n by n kernel matrix, comparing everything with everything else. And you've got a set of n discrete labels associated with the actual classes that are allocated to the training data. So the support vector machine is building, as you say, the maximum margin discriminant hyperplane in this embedding space. So the actual equation of the decision hyperplane then is going to be something like this. So this is a kernelized version of the equation of a plane in an n-dimensional space. So here theta is the weight vector for the decision plane. In other words, it's the orthogonal. It's the weight vector that is orthogonal to the plane of the decision hyperplane, and B is the bias offset. So basically, with an orientation and an offset, you can define any plane in this space. So this is what we're trying to optimize. We're trying to find, and basically anything on the actual classification function y is then something that allocates either a value of +1 to something that's on one particular side of that decision hyperplane and -1 to something that's on the other side. So that's just a mathematicalization of what we've seen. So the goal is to...
So what is this capital K?
So those are the kernels. So this is the kernel function.
But why is a hyperplane?
So
Hyperplane should be like linear. So
yeah. So basically, a kernel function is a function between two vectors.
yes, but I think on the previous slide you show some example kernel functions. They're quite non-linear.
Yes, yeah, that's the embedding space. So we're in the embedding space here, effectively. I mean, this is where,
okay.
yeah. So just in terms of understanding it, it's simplest to think in terms of actually having a concrete feature space at the moment without, worrying about particular form.
And the kernel induces the metric of the embedding space.
That's right, yeah. Although it isn't actually equipped with a metric, it's a Hilbert space, so it's called pre-metric space. So this would be an inner product if it were a linear kernel. This would be an inner product, and then it would simply be the equation of the decision hyperplane. So that is your decision function. This is what you're trying to optimize, and the training criterion is essentially a Lagrangian optimization problem. So Lagrangian optimization, you're typically minimizing some quantity. So the first line up here, this is the quantity we're trying to minimize with respect to all the free variables. So there's this vector theta that is defining the orientation of your hyperplane, B, the bias offset of that plane, and delta I'll come on to shortly, but effectively we're trying to minimize this quantity. Now, that is the kernel product of